Okay, so welcome back everyone. So continuing from where we left off in the last video, so we were discussing that there are a lot many sorting algorithms, but which one to use in which particular situation depends upon a lot of factors. So a lot of students actually come to me and they ask me that which is the best sorting algorithm. So the answer to this is basically that your choice of a sorting algorithm actually depends in that on many factors. So all those factors we have been discussing in the last video as well. And in this particular video, we'll formally define all those factors and we'll try to categorize our sorting algorithms based on those factors or properties so that you can better make a better choice in terms of which sorting algorithm to use depending upon your problem set and your the resources which are available. Okay, so the very first property on the basis of which we categorize our sorting algorithm is that how much extra memory is our, okay, let me just select the pen first. So how much extra memory is my sorting algorithm taking up? So if my sorting algorithm while running is not taking up much extra space, then we will term it as an in-place sorting algorithm. And in case my sorting algorithm while running up is taking up extra space which is more than order of log n, then my sorting algorithm will be termed as out of place sorting algorithm. So if I have to formally define, in-place sorting algorithms are the ones which do not require much extra space and use only constant amount of space or logarithmic amount of extra space. So let's say I have a sorting algorithm. Okay, let me just go to a. Okay, so let's say I have a sorting algorithm which I'm running line by line. Then in what all ways can my sorting algorithm take up any extra space? So one way in which it will take up extra space is that it might have some temporary variables defined in my code which might require some amount of extra space, but that will only take up constant amount of extra space. So I need not worry about that. So the second way in which my algorithm can take up extra space is that it can take some kind of auxiliary space. So let's say I have an input sequence which I have to sort. Then in some sorting algorithms, what they do is that they make an auxiliary space and they try to use this auxiliary space in order to sort my input sequence. So in case I have n number of elements in my input sequence, then what do they do actually is that they'll make an auxiliary array of almost the same size as my input, and they'll actually maybe they'll copy it down or in any way or in any other way if they're using that much extra space, then it is like taking huge extra space of the order of n. So whatever is my length of my input, it is taking that much extra space. Okay, so in that case, it is not an in-place sorting algorithm. In case it is taking only constant amount of extra space, then it is fine, it is in place. But in case it is taking more than logarithmic log n amount of extra space, let's say it requires some auxiliary array to sort it in whatever way it might require. We don't know as of now, but when we'll be looking into the sorting algorithms, we'll surely be able to, you know, uh, get to know as to why would we require auxiliary space in different sorting algorithms. So in that case, if it requires more auxiliary space, then it is out of place sorting algorithm. So third way in which my sorting algorithm can take up space is in case my sorting algorithm is making recursive calls to itself or some particular function. So in case I have a recursive sorting algorithm which is calling itself again and again, then on my stack frame. So whenever I call a function, then the parameters of that function are actually pushed onto the stack space. So basically, in a nutshell, whenever I'm making a function call, some amount of space is actually taken up on the stack frame. So if I have a recursive algorithm, then it is actually making function calls to itself again and again, and is taking up my extra space on the stack frame as well. So while deciding upon whether a sorting algorithm is in place or out of place, I also have to consider this particular factor, that what amount of space, extra space is it taking on the stack frame. So an in-place sorting algorithm which is recursive will not take more than order of log n extra space on my stack frame. Whereas out of place sorting algorithm, which is actually recursive, might take more than order of log n extra space on stack frame. So out of these, like these two situations that I've discussed, or let's define it more formally, that in case my sorting algorithm requires more than order of log n space, extra space, then it is out of place, else it is in place. Okay, so here I've termed it more formally and I've given this definition so you can better just note it down, that either the sorting algorithm might use some extra auxiliary space to sort the array or do the sorting in place by swapping the elements. So in case of insertion sort, bubble sort and selection sort, what we will actually see is that they will only swap elements and will try to do the sorting in place within that given input sequence only. They'll try to just swap the elements. Or other thing which merge sort do is that they actually take up some auxiliary space, and when they're trying to merge two arrays, then they will make a third array and they will try to merge these two arrays and will take up extra, and they will make up an extra array in order to merge these two arrays. So basically, they are not doing that in place, that means within that array only, and they are actually taking up extra space. So this is what this point discussed, that in case they take up an extra auxiliary space, then they are out of place, and in case they are doing the sorting in place only by swapping the elements within that given input sequence only, then they are in place. And the second way that a sorting algorithm can take up extra space is this, that our sorting algorithms might be recursive, hence might require some extra space on stack frame. If the extra space allocated on the stack frame while the algorithm runs is less than order of log n, then it is fine and it is termed as in-place sorting algorithm. In case it is taking up more than order of log n space on my stack frame, then it is an out of place sorting algorithm. Now you can actually note down this table. So here I have listed all the comparison based sorting algorithms that we have in our bucket list, which we will be studying, and these are the algorithms which are in place except the merge sort. So merge sort is out of place, and except merge sort, bubble sort, selection sort, insertion sort, quick sort and heap sort, all of them are in place, which is actually a good thing. And merge sort when done on an array is not in place. Okay, so moving over to our next property based on which we categorize our sorting algorithms is stability. So our sorting algorithm might be stable or it might be unstable. Now, what are stable sorting algorithms? So stable sorting algorithms are the ones which maintains the relative order of elements with equal keys. Okay, so what do this says? So let's say in case I have an array which has multiple elements, let's say these are the elements. So here in this particular array, I have two elements with the same keys, 3 and 3. So let's, in order to differentiate between the two, we put the index of this, which is 0. We attach the index of this to this, and this is 1. Oh, sorry, this is at present at the index 2, right? So after sorting, if this particular input sequence goes through my sorting algorithm and they are sorted, then the final sorted array would look something like this. Okay, so now after sorting, if the relative order of the elements with the same key, so and this this and this, if their relative order is maintained even after sorting, then they are termed as stable sorting algorithms. So what I want to say is that this particular element should come before this particular element. So this is the element which was present at the 0th index should come before the element which was present at this particular index, which is second. Okay, so in case I have more than two elements with the same keys, then also after sorting their relative order should be maintained. Okay, so if I have to term it more mathematically, then I would say that for all indices, for all indexes or indices, I and j such that I is less than j and ai is equal to j. So it says that for all elements whose keys are equal, then in the sorted list also ai should precede aj. So in sorted list also the ai should come first, because here also ai was coming before aj because I was less than j. So even after sorting in the sorted array also, whichever element was present at ai, that should come before aj. Okay. Okay, so now that we have got the basic idea of what stable sorting algorithms are, they are like very simple. So stable sorting algorithms maintain the relative order of elements with the equal keys. So now we'll look at all the sorting algorithms that are stable. So apart from quicksort, and heap sort, majorly all the sorting algorithms, comparison based sorting algorithms that we are going to discuss are stable. So you can like note this down. So bubble sort, selection sort, insertion sort, merge sort, all are stable. So when we'll be discussing these sorting algorithms, so then we will be starting as to why they are stable. But as of now, you just note this down in your like notebook, so that you have this ready for your reference when you are like going up for some exam. So now moving over to the third property or the factor on the basis of which we tend to classify our sorting algorithms. So the third one is adaptability. So adaptive sorting algorithms are the ones whose runtime complexity changes between depending upon the pre-sortedness of the input. So we actually discussed this pre-sortedness. What do I mean by pre-sortedness in my last video as well? So it means that how much my array is already sorted. So adaptive algorithms are the ones which have a lesser or which runs faster on the arrays which are already sorted, and they take more time in case my arrays are less sorted. So let's say if I have this array which is okay, like this will already be sorted. So let me just do this. So this particular array is like almost sorted, right? And whereas if I have this um, so this is relatively less sorted. So if I have a adaptive sorting algorithm, then that will take less amount of time to run on this and will take relatively more time to run on this. So adaptive sorting algorithms in a nutshell are the ones whose runtime complexity changes depending upon the pre-sortedness of the input. So an adaptive sorting algorithm will take less time when running on a list with high pre-sortedness factor and will take more time when running on a input list with low pre-sortedness factor. Uh, So if we see the list of adaptive sorting algorithm, then you will actually note that only insertion sort is the one which is adaptive. So insertion sort is the only sorting algorithm that are present with us, which is actually adaptive. So in case you are trying to choose a sorting algorithm to be applied in a particular situation where you will have mostly arrays with higher pre-sortedness factor, then you'll majorly want to use insertion sort only. Okay, so moving over to the next way in which we categorize our sorting algorithms, that is online sorting algorithms and offline sorting algorithms. But before we have a look at the difference between the online sorting algorithms and offline sorting algorithms, I would like to discuss a particular problem with you. So let's say you have a particular machine which is actually dynamically generating numbers for you. Okay. Oh, sorry. Which is dynamically generating numbers. And you, so let's say at a regular interval of say 10 seconds or 1 second, it is continuously generating some number. It is emitting out some numbers at an interval of 1 second each. So you want to design a sorting algorithm which keeps the numbers as they're coming in as sorted, but also have the capability to include the newly generated number in minimalistic time, as minimal as possible. So so let's say by the time 4 seconds are over, you have all these numbers with you and you have got this sorted in sorted order. And after this, if let's say after 1 more second, if a new number comes in, let's say 23, then you should not make much changes in your already sorted list. Okay, and you should have the capability to include this particular number which would fit in somewhere here, right? So you should have this much capability to be able to include in dynamically generated numbers into your already sorted list. Okay, so one another example of this can be that you are playing cards, let's say cards game, and you right now you are having 4 cards with you, and you have got them in sorted order. Let's say it is having this particular order. These are the cards which are present with you, and while you are playing the game, more and more cards are like coming to you. Let's say 2 cards come after every round, 2 new cards are coming to you, right? So you should be able to include these 2 cards at the right place wherever they fit in. So after every round, new cards will keep coming in, and you should be able to keep them in sorted order. Now here there are two main things that you must note down, that whichever process you will be taking help of in order to keep this particular list sorted, they should have two properties. One thing is that they don't pre-assume that they have the access to all the numbers all at once, because more and more numbers are getting dynamically generated, so they don't have the list of all the numbers at the starting of the algorithm. So they don't have, so that particular sorting algorithm should make consider this point that they are not having the access to all the numbers or all the elements of the input sequence at the starting, right? Of the input sequence at the starting. And the second property of that sorting algorithm should be that it should be able to do element by element sorting. So let's say I have this much part sorted, and whenever new element comes in, it should be able to get that sorted as well. Should be able to do element by element sorting. Oh, sorry. So it should be able to do element by element sorting. And one more thing is that it should not start the algorithm. So whenever a new element comes in, so let's say I've got this much list sorted, and let's say a new element, let's say king comes in. So it should not start the sorting process right from the starting all over again. So it should just make minimalistic changes only so that it can fit in king card at its right place. Okay, so it should not start right from the beginning. So now we can like head over to the main definition of what online sorting algorithms are. So basically online sorting algorithms were like produced just to mainly solve this particular problem of being able to keep the list sorted dynamically generated list sorted. So online sorting algorithms, they don't pre-assume that all the data or input sequence to be sorted will be available to them right at the starting of the algorithm. So they don't pre-assume this because all of the data is going to be dynamically generated. So they will actually sort element by element, or in some website I've seen it as that they do sort piece by piece. So they keep the available data or sequence always sorted and still have the capability to include the dynamically generated stream of elements in the sorted list. So whenever the new stream of elements is getting generated dynamically, it is able to include that in as well. So whichever sorting algorithm will be able to provide this much facilities, it will be termed as online sorting algorithms. But out of all the sorting algorithms that we are having in our bucket list, the comparison based sorting algorithms, only insertion sort, you'll be able to see that insertion sort has the capability to be termed as an online sorting algorithm, because what it do, while we'll be like discussing the insertion sort in detail, we'll be looking in the process in a more detailed way, but just for the overview process, you'll see that insertion sort tries to sort the array from left to right, element by element. So when it has processed the only one element, then it will keep this particular list sorted. After the second round, after it has processed the first two elements, it will keep the list till this part sorted, and after it has processed third element and then fourth element, it will keep the list sorted till this point only. So it is able to like able to provide all these, take all these points into account, that they don't have access to all the elements at the starting, because we are anyways in the insertion sort not looking at all the elements that are available after this point, if we have to like sort till this point only. And we are able to do element by element sorting going from left to right. Okay, so online sorting algorithm, in comparison based sorting, insertion sort is the only sorting algorithm that is having this capability. But there are a few more ways in which you can get the online sorting process done. So one is that you can use balanced binary search trees, which are nothing but AVL trees. So what you can do is that you can keep inserting in this as in when the dynamically elements are getting generated dynamically, you can add that particular element, dynamically generated element, to the AVL tree in order of log n time. And whenever you want to get that sorted list, then you can simply do in order traversal, which will take order of n. So this you must have studied this in the tree section. So AVL can help provide one such online sorting. The video will be categorizing our algorithms as internal sorting algorithms or external sorting algorithms. So before discussing what they are, we'll actually move on and discuss a problem first. So the problem here is that in case our data set is of a size which is larger than our main memory size, then we cannot load whole our data into the main memory. Hence our regular internal sorting algorithms cannot really work, or the regular sorting algorithms cannot really work. Now in case our operating system is actually supporting virtual memory concept, which you might have studied in operating system. In case you have not really studied virtual memory concept, then also it is fine. So virtual memory concepts say that you can go ahead and load a particular chunk of your data into the main memory, and when you're done with that chunk, you can swap out that data chunk, and you can load in or swap in the data chunk which is next required. So this is what, in a overview kind of a manner, virtual memory means, allows us to do. So let's say our data sequence or the input sequence is having 16,000 elements, and our main memory can only take up, let's say, 1,000 elements. Apart from all the processes that are running, it can only take up 1,000 elements. So our data set is actually having a size which is larger than our main memory size. Now if we are running regular internal sorting algorithms, then they might access data in this particular chunk. So what we'll do is that we'll load in this particular chunk into our main memory, process that particular data, and in the next line only it might access a data from this particular chunk. So what we will have to do is that we will have to swap out this particular chunk, and we'll have to load in this particular chunk of data, and later on it might have to access a data in this chunk. So there will actually be a lot of swap ins and swap outs that will be happening. Okay, so due to this, thrashing might happen, and the performance of our internal sorting algorithm, or the whichever sorting algorithm is actually running, will actually decrease or drop a lot. So what we have to do is that we actually thought of designing an external sorting algorithms. So external sorting algorithms, we thought that we will give them this extra power, that what all data it has to manipulate, or what all data it has to work with, will be made available in the memory, and will not do so much of swap ins and swap outs as we might be doing with regular internal sorting algorithms. Okay, so if we have to look at the external sorting algorithms definition, so in external sorting algorithm, the data set is so large that it cannot really fit into the main memory all at once. Hence what we do is that we divide our data set into small chunks and sort them independently. Each of the chunk we sort them, and later on we can combine all these sorted chunks or merge all these sorted chunks into one big sorted list. So what external sorting algorithm, as we will be starting later in the videos in a more detailed way, so what they try to do is that they will just load this particular chunk. So they will just load this particular chunk into the main memory, get this sorted independently. So let's say it is having only 4, although according to our numbers it should have like almost 1,000 elements, but let's say it is having 4 elements for the just for the example. So then it will sort this independently of what data is present in all the other chunks, and it will sort this chunk and will then write down this result back. So now we have sorted chunk. The data in this chunk is actually sorted. So hereby we'll repeat this process. Now we'll load this particular data chunk into the main memory, get this sorted, and so on. We'll repeat down this whole process and get all our chunks sorted in an independent way. So, and when we have all our data chunk sorted, we can run k-way merge sort, which we will be discussing later on. So we can like run a particular algorithm, we can say, that will actually merge all these sorted chunks into one big sorted list. So this is what external sorting algorithm can do. Okay, so in this particular algorithm, you must have seen that we are not actually referring to different chunks, and we are not actually doing much of swap ins and swap outs. Okay, so the performance of external sorting algorithm, if our data set is larger than main memory, would be comparatively higher when compared to the regular sorting algorithms which would be running in this case. So internal sorting algorithm, they require the entire input sequence or data set to be present in main memory. This is the definition that we have read. Now moving over to this point, so all the external sorting algorithms can work as internal sorting algorithms as well. So you must be like so it's this particular definition or this particular statement says is that if I have a set of external sorting algorithms, then they can actually, this set is actually a subset of the internal sorting algorithms, because a sorting algorithm which can work as an external sorting algorithm can of course work as an internal sorting algorithm as well, because external sorting algorithms are just having an extra power that they are actually referencing or sorting chunk by chunk and only referencing a particular part of the input sequence at one point in time. But like in, as I have said, that in different situations we might want to use different sorting algorithms. So we might want to use like quick sort in different cases, and in different cases, in case my data set is more than data set size is more than main memory, then I will have to use external sorting algorithms. Okay, so an example of this is modified merge sort that we will be discussing once we go ahead and touch this particular topic in more detailed way. So as of now, we have looked on to all the factors that can convince us on choosing or making a better choice in choosing a particular algorithm depending upon different situation and the resources that are available with us. So in the next video, we'll be looking at bubble sort and selection sort, and later on we'll be discussing all the sorting algorithms. Okay, so bye for now. Thank you.